Okay. What you've got then, if you if we look at everybody's results from that practical, you've all pretty much got a graph where if you're plotting the rate in the form of 1 over time, what's your actual unit for rate? Yeah, is actually going to be seconds to the -1, isn't it? Which isn't really a rate thing, but it, like I say, it's an acceptable estimate for this. And then your concentration of thiosulfate. I've done it wrong again. If I was going to do it like that along there, then you've pretty much all got a decent line like that. And if you compare that with your big A3 sheet, then what that means is it's first order with respect to the thiosulfate. In the assignment, this is exactly the sort of thing. No, you don't. No, WRT is my abbreviation, just because I'm lazy. And same with Concan for concentration. But you do use the square brackets. Yeah? Square brackets are the convention for concentration. All right, that is, we don't bother writing out the concentration of this, the concentration of that. It's square brackets. And it becomes particularly useful in the rate equation. And also when we're looking at equilibrium as well. So square brackets just mean concentration of. So we've kept the hydrochloric acid constant, varied the thiosulfate. You could, of course, do it the other way around as well. Keep your thiosulfate constant, vary the concentration of hydrochloric acid. You'd then have the order with respect to the hydrogen ions. And once you've got both of those, of course, you could then write a rate equation. Yeah, that rate equals K, and then you've got the rest of the expression by working it out practically. And that's why these are all described as, experimentally determined rate equations. All right. So what we've looked at then is really just the effect of concentration. And although you would expect increase in concentration to have an effect on rate, curiously it doesn't always. So I will leave that idea open for now. But the next thing that we need to go on to is to think about the effect of temperature on reaction rates. And this is where we have two things to consider. With the practical that you've just done, varying the concentration, one thing that you haven't controlled is temperature, of course. And we know how the temperature fluctuates in here. I mean, at least we haven't had to have the Bunsen burners on this afternoon. But, you get warm patches, cold patches, a breeze occasionally. So you do get variation in temperature. And, if we were keeping the temperature really constant, then you might have had, even more perfect straight lines. You would do that by, like we did this morning with the enzyme practical, using a water bath. If you've got to bear in mind the specific heat capacity of water means that it actually takes quite a lot of heat energy to change its temperature. So water stays much more consistent in temperature than air does. So using a water bath is a good idea. So what you're going to do for the actual assignment practical is that you're going to, rather than using a conical flask and just tipping stuff in, just as a sort of, it's a sidetrack really from where we are now, you're going to have a beaker of water, and then you have, the best idea is actually to stand it on a tripod ready for when you want to do the temperature one. But you have water in it, and you have boiling tubes in here. One of them will be held in a clamp stand, so let's hold that one steady. All right, so we'll put that over here. I'll just stick it on a tripod. Let's go the whole hog, draw the whole thing. We've got water in here, and this one would be the thiosulfate. Now behind it, you stick a piece of paper on the beaker with a dot, all right? So you can see the dot through that. In here, you have your hydrochloric acid, and you leave them to come to temperature, then you mix them. So you're keeping a much more constant temperature. All right, I'll come back to this, but obviously this is important because temperature influences rate of reaction. All right, now when you move on to doing the effective temperature, then you've already got it set up like this, and basically all you do is get the Bunsen under it, heat it to a suitable temperature, let it sort of reach a fairly stable temperature, then do the reaction, change the temperature again. And we have people having to redo this all over the place because the temperature one is really quite hard to hit the temperatures you want. You might be planning, oh yeah, the water starts off at 25 degrees, so you do yourself a results table, 25, 30, 35, 40, 45, 50. Yeah, that's not going to happen. Because as you heat it up with the Bunsen burner, all right, you say, oh, it's hit 40, you pull the Bunsen out and it keeps going up, of course, because you've got heat transference from the mat, from the glass of the beaker, and you can't get it spot on. So yeah, gets a little bit tricky, but you just have to plot whatever points you get on the graph. It works. So it works very well too. Now, basically then, as we increase the temperature, what do we expect to happen to the rate? It increases. We've done that with enzymes this morning. And the estimate is, as we described with enzymes, that for every 10-degree rise in temperature, you should get a doubling of the rate. That's for a lot of reactions that would happen at around room temperature. It doesn't apply to everything, so it's almost a useless piece of information, that. Rates of reaction are obviously very, very different. I mean, this one we would describe as a precipitation reaction. A precipitate is the formation of a solid in a solution. We've looked at all sorts of other reactions as well, so actually measuring rate is a bit tricky sometimes. What we're doing when we're changing temperature is changing the collision frequency. And the collision frequency increase will tell us how much the rate should increase. And I'm going to give you some bits off the ChemGuide website in a minute just to sort of explain this. But what I want us to get onto, and it's also got catalysts on it as well. This, for some reason, I tried to save paper, I think, and I've ended up with temperature and catalysts in the same handout. What I need to introduce, though, is the Arrhenius equation. So I'll give you these first. Okay, so this bit of ChemGuide, on the first side there just gives you this outline, pretty much what I just said, and then the explanation is underneath. So this idea of increasing collision frequency. And remembering back to yesterday, the idea of collision theory is that you only get a reaction when particles collide. Sounds obvious, but it's part of the explanation, so it's actually important. But if you look at numbers such as, well, you've got an example down there at the bottom, it turns out the frequency of two particle collisions in gases is proportional to the square root of the Kelvin temperature. If you increase the temperature from 293 to 303, in other words 20 to 30 degrees C, you increase the collision frequency by a factor of, and then he's given you the calculation there. So an increase of 1.7% for a 10-degree rise. Now, when we're actually looking at, the rate, if it doubles, well, that's actually not bad, is it? And you get a rate of reaction that's likely to double for about that number of increased collisions. So, okay, now if we move on to the bit over the page and the idea of activation energy, I mentioned this yesterday, that with the Maxwell-Boltzmann distribution, remember, you've got the energy of the particles, that sort of distribution, and if the activation energy is there, then only the particles colliding with that much energy or above are the ones that are going to react. And so you've got that repeated here. And The effect of temperature, of course, and I did start to introduce this idea yesterday. The effect of temperature on this, well, if that's at our lower temperature and then we increase the temperature, what we do is to give more particles more energy, and so the distribution moves over to the right there, and consequently we've now got our activation energy still the same. We haven't changed that, but we've got all these additional particles colliding with at least activation energy. So it's quite easy to explain the increase, you know, and it sounds obvious. Oh, you heat it up, there's more collisions, so there's more reactions. But it is about moving the number of particles with at least activation energy in their collisions to the right, so that you've got more of them. And you've got some, you know, some very clear little Jim Clark type graphs there to show you that. Now, where this then gets very, very complicated, and you can, the bit that follows on about catalysts and the rest of the handout, you can put that aside for now. Where this gets complicated is when we try and express this using the Arrhenius equation. But I think what I'm going to do is to get you doing the practical work on temperature first, because we've got the kit here and ready. And then I might leave the explanation of the Arrhenius equation to the beginning of the next session, so that it then runs into the assignment work, which isn't too bad, to be honest. And then it will, it'll make it a bit easier to understand what you're trying to work out for the assignment, I think. Okay, now the second practical then is based on the same premise as the one that you've just done. So it's still sodium thiosulfate, hydrochloric acid, producing sulfur, cross disappearing. This time, however, you have a slightly lower concentration of the thiosulfate. You've got 40 grams per decimeter cubed this time. And you're not changing that at all. And your quantities are slightly different. In fact, that actually gets diluted. I'd forgotten that. You start with 10 centimeter cubed of the thiosulfate and 40 centimeter cubed of water. So, yeah, we start with 40 grams, but diluting it down a lot. All right, I'll let you work out to what. You still use 5 centimeter cubed of dilute hydrochloric acid. And what you're going to do is warm the thiosulfate up, because that's the larger quantity. Now, when you add the hydrochloric acid, that's only going to be at room temperature, so it will bring the temperature down slightly. All right, now you've got thermometers to check the temperature with this, but the idea is, just let me check on the instructions, to repeat the experiment 5 times with temperatures in the range of 15 to 65 degrees. Chance of getting 15 degrees in here this afternoon, 0. All right. I mean, it was 26 degrees this morning, wasn't it? I think it's slightly cooler now, but of course, once you put the Bunsen's on, it's going to be warmer anyway. So you just have to, you know, do a selection of readings, you know, the best you can, really. The idea with the temperature is, they say take the initial temperature of the mixture. You really have to read it once you've mixed. All right, so you will measure the temperature as you warm the thiosulfate up, and you'll get a rough idea. But then once you take it off the heat, tip your hydrochloric acid in, swirl it, put it on the cross, but check the temperature at that point. Something like that. All right, so it's the temperature of the reaction, not the temperature you got your thiosulfate to, because you will cool it down a bit. Okay. And then you do it exactly the same way as before. You look at the cross from above, and when the cross disappears, you stop the time. And again, we can work out, I think we're doing rate. Yeah, we do 1 over. You haven't got a results table on this one, but you'll do 1 over time to get your rate, and you can do that against temperature this time and see what happens.